Sorry. All right. Class, I gave you several homework problems. I gave you the answers, but not the actual method of solution. Did you all see those? All right. Did you have any questions? Did you do them? Go ahead.
I had a question on the one. It's an antenna on an aircraft is being used as an electric countermeasure to jam an enemy radar.
Yeah.
And the gain of the antenna is 12 decibels.
All right. Let's go through. Is this 854? 85.5? Which number is that? 7.54?
Yeah.
This is out of a different book. So they give you a gain of 12 dB. I want to do these problems for you because these are all pertinent to what you could be expected to know. Go ahead. R is like 2 miles, is that right?
Yeah.
R is 2 miles. Go ahead.
Frequency is 7 gigahertz. Transmitted power is 5 kilowatts.
And they want to know the electric field at a distance 2 miles away, right? What type of they give you the gain of the antenna. They're assuming you're in the bore site or the maximum gain. So draw yourself a picture of this if you can. So you got an antenna. Forget about what its use is right now. You've got a gain of 12 dB. It's got a transmitted power here of 5 kW. Electric field is out at a range of 2 miles. So they're after E out here. But to get E, we're going to first get the power density there. Now, listen the way I do this. Make sure you can follow me. And this should be a seamless thing, regardless of what the gain is. First, that gain is in dB. So the first thing you have to do is put the gain in terms of a linear value. Now, in general, gain in dB is equal to 10 times the log of the actual linear gain, G. Everybody with me on that? So if I have 12 dB, in terms of the linear gain, I'll call it GL for now, that would be equal to that gain, 12 divided by 10, or 1.2, taken to the power 10. So it would be 10 to the 1.2. Does everybody understand that? All right. Now, I don't know exactly what that number is. Probably around 15. I'm not sure. You can check. You asked me about it.
15.85.
All right, so that's 15.85. Contrast that to the gain of a half-wave dipole, 1.64. It's much, much greater. This is focusing power. It's not super focused, but it's focusing power. And we can get to the actual approximation for the half, or I'll show you a way to figure out the actual beam width from this in a bit, but for now, it's a fair amount of focus. We want the E field, but we're not going to get the E field right away. First, we're going to find the average power density out here. And the way you get it is always take the transmitted power, right, divided by 4 pi r squared. Now that's as if it was an isotropic radiator. I keep telling you, think in terms of this. That would be the power density if there was no focusing, right? We have to still do R in terms of meters, and we'll do that in a second. And then it's times that gain, the linear gain. That will give me the average power density. We'll get this in a second. Y'all follow me on this? So that tells me what the power density is out there. Now that power density is actually equal to, because this is assuming a propagating wave in a very low loss environment, basically air. That's equal to 1/2 times the magnitude of the E field squared divided by eta naught. And eta naught is just equal to 120 pi ohms. Everybody with me? That's free space, 377, right? And you have to know this. So to get the E field, really what I'm going to do is take this quantity here, and I'd say the E field itself would be equal to the square root of 2 eta naught times the average power density. And now we go ahead and get these values. So I need to convert 2 miles into kilometers. What is it? 58 meters in a mile. I used to swim a lot. It's about 18 something, right, Mesa? You got Google. You can just.
3,218.
Yeah. So R here is 3,218. Did you say? 18 miles. Or sorry, kilometers. Meters. Pardon me. Meters. That means over here, my transmitted power density was 5,000, so it's 5 times 10 to the third times the gain, which is 15.85, over 4 pi divided by 3218 squared. Now, give me that number. Just put it down. Make sure you get these same numbers. You got it for me, Duncan? Anybody?
0.677.
Volt. I mean, this is watts per meter squared. I want power. Is that right?
Yeah.
Say it again. 0.677.
677.
Yeah. And that's watts per meter squared. Now, the E field, once you have that, what do you get for the E field? Hopefully it agrees. Huh?
Oh, that was the field.
Could you please give me this? I want this value. 5,000 times 15.85 over 4 pi, and then take 3218 squared. Divide by. Anybody? I want to try to fill into all the blanks, so to speak, so I don't get a repeated question about that.
I got 0.000609.
0.000609 watts. So it's really 600 and, or 4, 5, 6. So it's 609 microwatts per meter squared, right? Whoever said that? Who said that? Did you get that? That's right? All right, so then E comes out to, give me that to me again, people. Duncan?
0.677.
0.677 millivolts or volts?
Volts.
Volts per meter? Can you check that? Was that what the answer says?
Yeah.
All right, so that's how you get it. These are good problems. They're straightforward. There's nothing tricky. Again, the mile conversion to meters is something you have to be adaptive, and I would not ask you that without providing some, conversion for you. And the second thing is make sure gain in dB, you use linear gain in these equations. Don't put 12 in there. That's a common mistake. Okay? Next question, Duncan. You got another one for me? Or somebody else? I'd like to do them all, because there's the last one's the one I was most curious about. But we might as well do the next one. So this is a standard problem. What's the next problem? Are there any other questions about this one? It's really just being familiar with dB and changing miles to meters. That's it. All right. Somebody asked me about problems. I felt bad I didn't give you enough problems last time. I'm going to make sure I give you plenty of problems with answers or solutions or both this time. Next problem. Go ahead. Anybody? It's sequentially. The next one after that. What is it?
A lossless half-wave dipole.
All right, hold on. So now the actual dipole is lambda over 2 is the length of this. This is important. Go ahead. Lossless, which is important. Go ahead.
Yeah. It's driven by a 10-volt
Oh, yeah.
50 ohm source.
So they got a source here, and this is plus to minus 10 volts. There's 50 ohms here. The antenna itself, Z antenna, has 73.2 plus J42.5 ohms. Remember this, all right? Now that's a half-wave dipole, but keep going.
Determine the electric field intensity at a distance of 10 kilometers in
Okay.
a plane perpendicular to the antenna.
R equals 10 km. So this is at 90 degrees. It's where the maximum gain is. And they just say it's, and what do they want, the electric field again?
Yeah, electric field intensity.
So they still are after the electric field out here. I'm going to show you 2 ways to get this. I want to make sure you know how to do them both ways, and you can do it efficiently. So the first way is the basic equation for electric field from a half-wave dipole is just equal to J60, right, over R times e to the minus j beta r. Then it's going to be times the cosine of pi over 2 cosine of theta over the sine of theta. Now that's an angular function, but when theta is 90 degrees, that angular function is 1. Do you follow me on this, class? the cosine of pi over 2 cosine of 90 degrees divided by sine of 90. If you just look at this, well, what's the cosine of 90? It's 0, isn't it? So if I have the cosine of 0, that's 1, right? Divided by the sine of 90, that's 1. 1 over 1 is 1. Do you follow me on that? So it is 1. Even if you wanted to calculate it, it would be 1. But nevertheless, it's 1. So really, when I'm taking a look at the electric field magnitude, I can just say it's equal to, the magnitude of that is 60 I. There should be an I in there. Sorry about that. 60 I over R. That's what it is. So how do you get I? And this is something that, when I give you this, you got to be able to get I. Only thing you do is take the 10-volt source. Then you have 50 ohms of series resistance, and then you put the antenna impedance, which is 73.2, right? 0.2, and then it's going to be plus J 42.5, and we want to figure out that I, magnitude. Well, that I is straightforward. I don't mean to be working real fast, but this is basic stuff. Right? So if I want that current, I just take the voltage 10. Please get this current right. And I want the magnitude of the current divided by the magnitude of 50 and 73.2. That's going to be 123.2 plus J 42.5. And remember, I want a magnitude of that right there. And I want what I is. Can you give that to me? It's 10 over 123.2 plus J 42.5. That's 42.5. What do you get for that? You got it?
0.0767.
0. Say again?
0.0767. An angle of.
No, I don't need the angle. I just need the magnitude. Remember that. Forget the angle in this one. Okay? You all agree with this? All right. Now, if I want the electric field, I can go right to this equation. I can go ahead. And I can see that's going to be 60, right? Times that I, which is 0.0767. And divided by R, which is 10 to the 4th, and I can get the electric field. Give me that value that way. I want to do it a different way. Can somebody just tell me what it is? See if it agrees with the answer and the solutions. Guys? Did anybody download MathCAD and try it, by the way, in here? PC MathCAD? Not at all. I was hoping somebody did. You'll see that this thing is made for these problems. It flies through them. You can do these things that fast. 0.46, go ahead. No, just meter. Does that square with the answer?
Yeah.
All right. Now that's one way. Another way to get it is this. That's a half-wave dipole, right? The max gain of this, the gain, or really directivity, but I'm going to use gain, would be 1.64. Everybody follow me on this. That's the gain of this dipole. You need to do it this way too. You need to be able to do it this way. Trust me. Now, if that's the gain of that antenna, I've got the current, right? I've got the current. How do I calculate the total P radiated, the radiated power, anyone? If I have the current, what is it? Yeah, and I like the 1/2 in front of it because this is a peak current, not an RMS current, right? So it's 1/2 times the magnitude of the current flowing through the radiation resistance squared times R rad. What is the radiation resistance of a half-wave dipole? 73.2 ohms. All right, that accounts for all the radiated power. Agreed? So it's going to be 1/2 times the magnitude of the current, which is 0.0767, squaring it, times 73.2. So tell me the total radiated power here.
I got 0.215.
Anybody else confirm that?
Yep. Yeah.
And 215 watts, right? Now we're going to find the amount of power at the point where we want the electric field measurement. Follow me? So that power out there, I'll put it here. The power this is going to be an average power density, would be equal to this total power, P rad, the transmitted power, radiated, over 4 pi r squared, r is going to be 10 kilometers, times the gain, 1.64. Go ahead and give me that. So we've got the radiated power, we multiply it by 1.64, right? And then divide by 4 pi r squared, and r squared is 10 to the 8th. What I like about MathCAD, it's WYSIWYG. So I've got that formula, I change the values, bang, it gives me the answer. It's very quick. Anybody?
0.28 nanowatt.
Times 10 to the minus 9, and that would be watts per meter squared. Anybody confirm that?
Yeah.
Okay. Now, that's the power density, right? That's in watts per meter squared. That's equal to 1/2, right, times the magnitude of the E field squared divided by eta naught. And therefore, eta naught, therefore E, I'm sorry I'm putting it down here a little low, would be equal to this value times 2 times eta naught, square root of it. So it's equal to the square root of this power density, P av, right, times 2 times eta naught, or 120 pi. Now give me the E field. Use that calculator.
461 millivolts.
461, you say millivolts? Then that should be millivolts. Is this right here?
Yeah, you did not know.
It is millivolts? Oh, sorry. Okay. Times 10 to the minus third volts per meter. So those two should be in agreement within the margin of error we have for rounding and stuff like this. That's how you get this either way. So no matter what I supply you with, you can work backwards and get anything. If I give you the power density or electric field or H field out there, you should be able to work back and tell me what the voltage was here that would cause that. You follow me on this? So be able to do these things forward and backwards and understand all facets of it. Don't memorize just one formula and say he'll give me an A and B and I need C. It won't work that way. You have to understand what's going on completely. Got it, everyone? Last problem is a good problem. I think this is the last one, isn't it? Or is there one more interim? All right. Go ahead. We'll do that. Because this sets me up for what I wanted to do today after I'm do these things. All right, what's this one?
A wire carrying a milliamp current.
Is it above a ground plane?
Yeah.
This is the one I want you to focus on. This is a great problem. This is the kind of problem I typically give on exams. So hear me. I have now a conducting ground plane, right? If you look at this problem. Now I have a wire. The wire has a length of 1 meter. It is above the ground plane, a distance d, and d in this case is equal to 1, is it centimeter, right?
Yeah.
1 centimeter, 10.01 meters above, right? And they want to know what the electric field, I think it's electric field is, at a distance of 3 meters above here. They want the E field. Follow me on this? Everybody? Now they give you a frequency of operation here, and is that 10 to the 9th hertz or what?
Yeah, 100 megahertz. So.
Oh, it's 10 to the 8th. 10 to the 8th hertz. Okay. For the record, give the current an assigned direction. Call that I. And I is 1 milliamp, okay? Now, here's the one thing that's a little bleared here. Normally when you do a problem like this, the first thing I tell people to do is determine the length of the antenna in wavelengths. So if this is 10 to the 8th, lambda, the wavelength would be C over F. C is 3 times 10 to the 8th, over 10 to the 8th is 3 meters. Everybody follow me? Now this is 1 meter. This is in that gray area. 1 meter long is not much less than a wavelength, but it's not a half wavelength either. Do you all follow me? It's in that gray area. For this purpose, usually, even though this isn't exact, it's still pretty good. If you think about what's the difference in gain between a short dipole and a half-wave dipole. What's the gain of a half-wave dipole? 1.64. What's the gain of a short dipole? 1.5. Not a lot of difference. If you're right in that region, about a third of a wavelength, you're going to get about 1.5. It might be just slightly less, but it's close to it. Do you follow me, class? So if you default to a short dipole, you're going to do fine in this one in terms of the approximations for what this wire actually resolves to. It looks like a short dipole antenna, but you'll notice there's a current in this direction here. What happens to the image when we go down a distance d, class? It's parallel to the ground. How does it image? Opposite direction, right? So that means the current down here below it would be in this direction. And that would be the image, correct? Now we need to find the electric field here caused by both of those. Here's where phase becomes critical. And I want you to see this and appreciate why I'm telling you this. In general, the electric field from a short dipole, the general equation is J eta beta I times L. So it's the magnitude of the current proportional to the length of the antenna as well. Then it's divided by 4 pi r. That's the radial distance. Then there's the function e to the minus j beta r. That's a phase function that becomes very important in this problem. Usually we disregard it if you have a single antenna. But if you have more than one antenna, you can't. You have to add them both magnitude and phase together because this is like adding complex numbers. Then there's the sine of theta. And that would be a theta. Now, this one already has the actual observation point perpendicular to the antenna. Do you all follow me on this, class? If it's perpendicular to the antenna, it's the sine of 90 degrees, or it becomes just sine theta becomes 1. Follow me? So for this problem, you can get rid of the sine. Now we take a look at this, and I'm going to write the electric field for both of these antennas. We'll call this antenna 1 and this antenna 2, and we're going to add them together. So the electric field from antenna 1, and you don't need to worry about theta. We know the electric field from this one is going to be either that way or that way. It doesn't matter, but it's perpendicular to the direction of propagation, and it's parallel to the ground. And the electric field from this one is going to be oriented, if you think about the currents in the opposite direction, so it's going to have this sense to it. You all follow me? All right, so when we do this, here's how I do it. I'm going to take out a bunch of stuff. First, the J, eta, beta here are the same. And y'all give me that 1 over 3 meters plus or minus a centimeter is about the same thing? All right, so I'm just going to take the R factor. I'm going to go ahead and put I there, and that's going to be the magnitude of the current, and L. Then I'm going to take the 4 pi R here. All that's going to come out in front. Now, the thing I need to include is the phase terms, right? The first one is here. I have E, and it's going to be J minus J beta. Now, the R from this one, I want you to take a look. This distance to this point of observation is 3 meters, but it's going to be minus that small d, right? Follow me? Everybody see that? So now I have minus j beta, and it's going to be r minus d. But then the other one has a minus sign in front of it. The sense of the current is going minus, so I pulled out the current magnitude. I leave the minus sign there. Follow me, class? This is the one down here. And it's going to be e to the minus j beta, but now that's going to be r plus d. Do you all see that right here? Right? Now, some of you are savvy. You can see what I'm going to do. I'm going to still leave all that factored out. And can't I factor out an e to the minus j beta r from both of these and pull that out in front? Do you all see that? So I'm going to go ahead and factor out put the L here, e to the minus j beta r here, and then I get rid of it here, and I'm left with plus j beta d here. And I'm left with minus a minus j beta d here. Okay? Now, if you just take your calculators and plug in the numbers, into this equation, you'll get the correct answer. If anybody wants to do that, you can. We've got eta is 120 pi beta, just for the record. Since the wavelength is 3 meters, beta is 2 pi over 3 then, right? That would be 2 pi over the wavelength is beta, correct, class? After that, I've got I is 1 milliamp, and you've got the length is 1 meter. You have 4 pi r is 3 meters. So you have this, right? This is a phase term you don't need to worry about. It's these phase terms you do. All right, now if you actually calculate that, if somebody would do that for me, I'd appreciate it. Now I'm going to reduce this down in complexity. I'm going to say this can actually be equal to j eta beta times I times L over 4 pi r. The e to the minus j beta r I'm going to disregard, but I'm going to leave it in. I don't care about that. And then for this, do you all see how this basically is what? Well, what's sine of theta? It's e to the j theta minus e to the minus j theta over 2j, isn't it, class? Y'all see that? How this is really 2j times the sine of beta d? How many see that right there? Right? Y'all see it? So I can just put this as 2j times the sine of beta d. And this will be the right answer. Now, if we're worried about the magnitude of the E field, and that's the only thing we're really worried about, unless I tell you differently, then all it's going to be is simply eta beta IL over 4 pi r times the sine of beta times d. And you're going to note that sine of a small number is about that number. So you can literally just take beta d out in front if you want. But go ahead and give me what this is. Either this or this. Yes, yes, you're right. There is a 2 right here. Thank you very much. This 2 would still be there. Thank you. You're right. What do you get for this? We've got beta, we've got d. Remember to do that in radians, not degrees, your sign, right? Because beta is in radians per meter. So it's 2 pi over 3 times 0.01, right? I don't know what it is, but it's small. And then do that times eta beta IL times 2 over 4 pi r. I want to make sure everybody sees how to do this. This was the good problem. This was the challenging problem.
0.877 millivolts.
Can you see what the answer is? Is that square with the answer?
Yeah.
All right. 0.877 millivolts per meter is the E field. And that's a good problem. Because when I give problems on a test that are like this, I have a lot of people that are really confused on how to do the imaging correct. That's the key to this one, all right? Now, if for whatever reason this was this way, right? It would have an image positive this way, right? Then you would have effectively a short monopole, which is like a dipole, or short dipole, correct? And you would do it that way. Just make sure you're square about the way to do these problems. Now, was there another problem that I gave you or not on there? All right. Now, there were some plots above there where I asked you to just go ahead and take a look at the plotting. You can do that fairly quickly on MATLAB. I did mine on Mathcat. I was hoping somebody would do it because it's so much easier to do it, in my opinion, on Mathcat. I've used Mathcat and MATLAB for the last 30 years. And when it comes to quick stuff, getting an answer, I use Mathcat all the time. I go for that over MATLAB. And it's much more versatile and much faster. MATLAB, when it comes to real number crunching, if you want to do something with a lot of matrix operations or something like that, then MATLAB's the way to go for your prototype. Or these days, I don't use Octave, but I know that Octave's a free version of that. And it's a little slower than MATLAB, but it'll do it. I know some people use Python for these things. Python is a little slower than all of them, but it will get the job done. I know Python's free too, and so is Octave. So,
Python's way faster than Octave.
Okay, I don't.
Yeah, Python's on par with MATLAB in terms of speed.
Okay, I am clueless on this. I don't know. Yeah.
I was going to say, plugged in that equation.
What? It works? Yeah, it comes out with the same value, no matter which you use. This was the one you'd probably use. You wouldn't use that identity, but it's nice to put the sign identity in there. It makes it easier and quicker. All right. Now, for today, we're going to go through the Friis equation entirely, and I'm going to show you how to actually figure out the power extracted. I don't think I gave you a problem with Friis last time. I was covering it, right? I'm going to go through it again and get to the bottom line. I have a question before I even do that. And this is, I'm going to be very fair about this. I need to give you a quiz. I will give it this Wednesday if you want it, or I'll give it the following Monday. All right? I want you to think about it for a minute while I erase the board. Which would you prefer? But what I'm not going to do is give anybody an absentee on Wednesday because they're going out on the beach or something. If you miss it, it's gone, unless you have a university-approved excuse. So I want you to just think about that, because I get a ton of emails. Oh, Dr. Baginski, I can't be here. I'm going to the beach. I'm doing this, that. Well, good. You're doing this. I'm happy for you. But if you cause me to do a makeup just because you wanted to go to the beach, you're out of luck, pal. All right. Now, if you want it on Wednesday, you count with me, all right? Want it on Wednesday, one hand up. Wednesday. Count with me now. I got 2, 4, 6. Just let me count now. 2, 4, 6, 8, 10, 12, 13, 14, 15. Is that right?
15?
I got 15. All right. If you want it on Monday, raise your hands. All right. Count with me now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Is that right? So the 15s have it. Listen, I gave you the choice. Don't get mad at me. Beat one of your friends up. All right, so you were having a quiz on Wednesday. So if you're going to the beach and you're not here, you get a 0. Just so we're absolutely clear and there's no more of these crazy emails. All right? I don't care when you get it. I just want to make sure if it's going to be on Monday or Wednesday, everybody's clear on that. I'm not giving a makeup because you're going to go party somewhere. I'm not. That's it. So back to the real world and the Friis transmission equation. So this is Friis. Friis T equation. You know, this class isn't bad about this. I got another class of 100 people that are engineers from everywhere. It's 3810 there's just too many of them. I had to teach that section. And I have got more unbelievably lengthy excuses why they can't be here. And I asked them to get a university-approved excuse, and then crickets. It's like, I can't get that. Well, you're going to get a 0. All right, Friis transmission. Here's what the problem is, and I'm going to talk about some aspects of it that are important. I said it was a microwave length that can be anything. You're going to have a gain of a transmitter here. This is your transmitting antenna. In here, we're assuming that we transmitted power, a certain amount of power. Just call it PT for now. This has a gain. Now, we're going to assume that this gain right here, it's a function of theta, right? It's a function of phi, possibly. This is just an antenna. That's all I'm putting here. This just says transmitting antenna. That's all it is, transmitting antenna. It's at a distance r from another antenna. Now, this antenna does not have to be aligned for maximum amount of gain or anything. It could be misaligned, but it's got another antenna up here, and this is going to have the gain of the receiving antenna right here. And now I'm going to find out the power received. That's what I'm after. And if that's so, the way it works is this. When I talk about the actual transmitted power, PT, that's transmitted power, over 4 pi r squared, that's my starting point. That's what the power density is from this antenna if it's isotropically radiating that power. Everybody got that? Now we multiply it by the gain function. The gain itself is a function of angles, so I'm just going to leave it as a function of theta. We'll call this theta. Measured between the axis of the antenna and the vector r. If that was a short dipole, the gain would be 1.5 times the sine of theta. If it was a half-wave dipole, it would be 1.64 times the cosine of pi over 2 cosine theta over sine theta. Squared. I should say sine squared, too. Both of those would be squared. We have that. Now, that power is launched. It comes in contact with this antenna. This antenna has an area or an aperture effective area is equal to lambda squared over 4 pi times the gain of the receiving antenna. It's important to know that. It's lambda squared divided by 4 pi times the gain. That's the effective size of that antenna in meters squared. It's how big it electrically looks. So now I take this and I multiply it by lambda squared over 4 pi times gain of the receiving antenna, and that is a function of angle as well. And it's a function of really this angle. Call it theta 2. Call this theta 1. Now that's how much power is received. In the way they normally do this thing, they try to make it compact, and they say that this is the power received right here. They say power received divided by power transmitted, and this is sort of the goodness of the antenna I was talking about, is really just going to be gain of transmitter, gain of receiver, times lambda over 4 pi r squared. Keep in mind these gains are a function of angles. There's a couple problems I'm going to give you in the book. I think, did I give you those problems? Okay, I did. Were there any questions about them? It's pretty straightforward because the only thing you have to do is adjust for the gains. The radial distances are given, and the power, I think, is pretty straightforward. I think. As I recall, those problems were just straightforward on these. So that's the power receiving. Now, that works in the ideal sense if the antennas are aligned. Let me get to this problem. So if I have a dipole antenna, this becomes important. You see this. If I have dipole antennas, two short dipoles or half-wave dipoles, they're aligned for maximum gain, they look like this, right? Now here's something that happens. One of these two can do this. When that happens, all of a sudden the angle that this makes with respect to the rate, this vector here, r, is less than 90. Do you follow me? Take the near angle too for that. All right, when it goes to this, just tell me what happens. That's max gain, right? What happens to the gain or the power received when I do this? 0, right? Because now nothing's transmitted up and down the axis of the antenna and nothing be received. By the way, the transmitting pattern of an antenna is the same as the receiving pattern through a theorem called reciprocity. The same way it sort of distributes power as it's radiating is the same way it receives power. So it doesn't receive any power down the ends of the antenna. And its max power received is when it's coming broadside. That's the way it is. All right, here's another thing that happens. Now that you got down because that's taking care of this with these gains, right? Because that angle is with respect to the radius vector, correct, class? But here's another thing that happens. This is polarization mismatch. Well, here they're aligned. The electric field from this one generates a current in this direction on the receiving antenna. But what happens when I do this? All of a sudden, when I get it like this, the electric field from this one is horizontal. This receives vertical signals. So there is no component of the electric field from this one transmitting in this direction, and it's 0. The way it actually works, and this is called polarization mismatch, it happens all the time. Almost invariably, you can't help it in the real world. You're going to get some polarization mismatch. It's just reality. So the way it works is you take the cosine of the actual angle and square it. So if you have two antennas, I'm going to draw them on top of each other. If this is one, and this is the receiving antenna, and this is the tilt between them. Now remember, that tilt is in this plane. It's in the plane parallel. Oh, boy. If they are both vertical, right? The plane vertical, horizontal this way, whatever you want to call it, it tilts this way. It does not lean this way and that way, where there's a projection in the radius vector, all right? There's no projection of the tilt angle in direction of propagation. Does that make sense to everybody? So when it tilts this way or that way, that's where that cosine squared comes in, all right? Now here's a little bit more complicated thing. I want you to follow me. If I have two antennas like this, and I take one and I skew it upwards, remember they're still aligned vertically, right? Now the gain of this one and the gain of this one isn't going to be max gain. Both of them are going to be dropped down, right? By the cosine, or it depends what it is. If it's a short dipoles, by the sine squared of the angle between the vertical direction of the antenna and the radius vector r, right? Now if I take these two and then I tilt one like this, now you've got to also adjust for the cosine squared of the angle of tilt, all right? It would be the angular difference between the vertical and this angle right there. Follow me on this one, class? Everybody see that? So this, and then all of a sudden this would cause a polarization problem. Now, if I did this, that's not polarization. That is just pure gain, all right? Follow me on that? Because now the lean is the thing you're worried about, all right? But if I did this, now listen, now I'm going to tilt it inward like this a little bit, right? And then if I did this, there's still going to be a polarization mismatch. Do you follow me? You still need to get the tilt angle difference, and that's very important. I will test you on that. And people need to know this. I can tell you this much, that most of the time when you're talking about microwave and radar, for important things, it's circular polarization. Now, circular polarization implies you have an aperture antenna, and aperture antennas aren't affected by the tilt angle problem. All right, right circularly polarized, left circularly polarized, they don't have problems with tilt angle at all if it's circular polarized, or if it's something where you get an actual dish antenna that's a circular dish, or I say, it has no difference, there's no ellipticity to it. That's important to know. But the problem with a lot of this stuff is that so much these days with small companies, when they actually string antennas and do stuff, they have people doing it that aren't fully aware of some of the problems. So they'll mount an antenna like this, and a couple miles away they'll have an antenna like this receiving, they don't get anything. Well, for starters, they're not aligned, all right? That's important. And also, by the way, if you want the maximum amount of signal received, then have it vertical, perpendicular to the ground, not planar to the ground. That's another thing. Don't have it horizontally polarized, make it vertically polarized, and try your darndest to get them aligned if you're making any kind of thing where you're communicating short range. Has anybody ever done this where you actually had to make a communication link? Anybody? Nobody? Well, you probably will at some point. And it's common. I mean, how many guys here hunt? Anybody? You guys hunt? Well, I guess cell phones make that, you don't even need it now because cell phone coverage is so good. Back in the old day when they didn't have it, you'd get things where they'd put a walkie-talkie. You know what that is? It's communication. I don't know if you do or not, but they put one out there in the field somewhere where you're going to be, and because that way you can call in if you shot something or you're lost or something, somebody could come and pick you up, because it would be out 10, 15 miles on foot, and that happened. And what you don't know is kids don't know that talking this way when the antenna is aligned that way, it doesn't do any good. You have to have it vertically aligned. Anyway, so that's the tilt angle business. It's covered in this book. Huh?
Which way is tilt measured from? Like, is it measured
It's only relative to two things: the direction of this antenna, the projection of this antenna on this one. So it's a measurement of the difference, the small angle difference. All right.
Okay, so the smallest angle is the
Yeah, and really, because really you square it, it doesn't really matter. You get through the negative sign if you get a negative value. All right, next we're going to talk about, that's Friis in a nutshell. Now, how much power can you receive? This is important. Actually, we talked about P received here. This amount of power is received, but this is the problem that's disturbing. That's not the amount of power you can actually get out of that second antenna. That's how much is received. At best, you can get half of that power out. The other half is re-radiated, and I'm going to show you how. And this is something that, depending on who teaches some of these courses, they don't go over the finer points always. I'm sure Riggs and Wentworth will. All right, so now we're going to do this. Hear me now. We're going to assume I have an antenna here, and I've figured out through the Friis equation how much power is received. So I know what's power received is there. I've got that, all right? So what does that power received really mean? Well, I know the antenna itself has an antenna impedance, right? So here's what happens. We take this antenna system, we say it is equivalent to some voltage that we term V open circuit. That's on the antenna, it's the open circuit voltage that we don't know yet. And then there is going to be the impedance of the antenna. And that's going to be the R of the antenna plus Jx of the antenna. That's the imaginary part, like 73.2 ohms plus J 42.5 for a half-wave dipole. Follow me on this? And by the way, this doesn't have to be positive. It can be negative as well. That's irrelevant. But that's internal to the antenna. There's your antenna. Now out here, you're going to hook a load, right? And this is the thing. When the load is equal to the conjugate impedance of the antenna's impedance, you get maximum power transfer. This equation, where I get P received, is assuming a matched load. They don't say that, but it is. So the matched load would be same R antenna, right? But then it would have a what? Actually, it'd be a capacitor there. It would have minus JX antenna here, right? And this is the load. This is the observable load. Now, y'all notice why it's conjugated, right? Because if you put the conjugate of the antenna impedance, this and this cancel. Follow me on that, class? And now the actual current that flows here, I, right there, I will be equal to the open circuit voltage, right, divided by 2 times R of the antenna. And that will be I. Now that's the current that's flowing in this circuit. Remember, this is assuming that's the P received under the best case. If you have a matched load, that's how much power you can receive. Not absorb, not take it into a resistor, but that's how much it can receive. So how much power is this? Well, I have 2 resistors, right? So the power received would be equal to 1/2, right? And then it's going to be times I squared times the resistance, which would be, in this case, 2R, right? Or 2R antenna. And that's going to be equal to 1/2 times VOC over 2R antenna squared times and that means I get, one of those cancels, I get 1 over 4, or VOC, sorry, VOC squared over 4 times R of the antenna. And that's equal to the P received. Please just bear with me. Do y'all follow me on that? R2, see, this right here is VOC over 2R is the current, right? When I square it, one of these cancels, or this cancels one of these, and I'm left with simply 2R of the antenna. Do y'all follow me, class? Can you see this in the back? All right. Now that's P received, right? I'm really after the open circuit voltage with this equation, so I can see that the open circuit voltage here, and this is important, V open circuit is actually equal to the square root of 4 times R antenna, so that's the real part of the antenna impedance that you're using, times the actual P received. And P received is calculated from Friis. So that gives me the open circuit voltage. Now the reason I'm saying this is in the real world, you need this quantity right here to solve your problem for how much current or power is being utilized by your load. Remember, this P received is from Friis, right? It's the best you can actually receive, but you can only at most get half that power out. Now, what you do next is important. Next, we say that suppose I have a half-wave dipole and it's receiving 2 watts. But attached to that half-wave dipole, in ideal, I attach a different load. Then I do this, really. I have my V open circuit that I know how to find. I have the antenna impedance, so I have R antenna, and then plus JX antenna, right? That's the antenna impedance. Here's where I attach my load. Now I put my load in there, and now I can get either the current through the load or the voltage across the load. Do y'all follow me? And you need the open circuit voltage to get that. Everybody see that, class? And we get the open circuit voltage using this equation. P received comes from Friis, okay? Now something else I'm going to tell you. It's not brought out in the book. If you think about this, because under the ideal circumstances, this is an external load to the antenna. The most power we can actually dissipate would be half of the total power. Do you all see this? This R antenna right there, that's part of the internal resistance of the radiation resistance of the antenna. When that antenna actually receives power, it is still going to re-radiate, or there'll be power reflected off of that. And that has to do with the radar cross section of the antenna. And there's more on that later. I'm about out of time. I'm going to cover radar next time, all right? I'm going to give you problems on this one. So we do have a quiz Wednesday based on a rather split vote. But what I'll do is I'm going to quiz on the antennas, on something with antennas, probably in the last 2 or 3 homeworks, okay? You're going to have to know what impedances and how to get power and Friis and this right here. Okay?